Hi. So now we're ready to play a little bit with circuits and to test our understanding of currents and voltages. So we know how to calculate in simple circuits the currents and the voltages, but it's easy to lose track of the physics when we do those problems, and we just calculate values of currents and voltages, but we lose some intuition about what happens in the circuit. So here's a type of problem that forces us to think really about current and voltages, and to understand what happens to a circuit when you change it by adding or subtracting, removing resistors. Okay, so we start with this simple setup here. We have just a battery here with an EMF E, so that's the voltage of the across the battery, connected to two light bulbs. Um, Here, there's no current that flows in this branch, so this light bulb is off. And then you have some current flowing here, obviously, and you have this light bulb is on. So the question we ask is, if let's say we take this switch and we close it, thereby creating a new loop, what happens to the brightness of light bulb A? Okay, and brightness of a light bulb is just a measure of how much energy per second is emitted by the light bulb. So that's just the power. So what we're asking is, when we close the switch here, what happens to the power delivered to this light bulb? And the light bulb is just essentially it's just a resistor. So no, we use light bulbs here, but they're just resistors. Light bulbs are just nice because you can visualize right away what happens to the currents and the voltages by looking at how bright the light bulb is. So if I close the switch here, uh, will the brightness of this light bulb go up, increase? Will it go down? So will it become dimmer, or will the brightness stay the same? So we have three options. The light bulb glows brighter, dimmer, or the brightness does not change. Recall that for power in a resistor, we have two forms of the equation. We can use either Ri square or delta V square over R. For these problems here, you can assume that the resistance of all the light bulbs is the same, although most of our conclusions don't really depend on the exact values. But just if you, it helps, just imagine that the resistance are the same. So think about that for a second. I close the switch here. What do you think will happen to the brightness here? And again, if you look at the equations here, another way of asking the question is, well, in this branch here, when I close this switch here, in this branch, will the current go up? Will it go down, or will it stay the same? And what about the voltage? Will the voltage go up, go down, or stay the same? So think about that for a second and try to guess the answer. And think about what your argument is. Okay? Now, ready? Okay, there are two arguments that people make usually. For first of all, before we do that, obviously here before you close the switch, the current goes this way, and it's just given by E the EMF here divided by R, right? So that's when the switch is open here. So there's only one loop. Okay, now we close the switch. So here's the circuit. Now I've closed the switch, and now there's the two light bulbs are on. So the first argument, I focus on this light bulb here. This is light bulb A here. Some people say the following. Because we close the switch, the current that flows here now will split. Some of it will go down here, some of it will go that way. Therefore, because the current is split, there's less current in this light bulb than before. So therefore, the brightness of this light bulb has decreased when you close the switch. Okay, so the argument is the current splits, so no a small current in that lamp, light bulb, and therefore the brightness went down. A different argument is this. If you look at the voltage applied to this light bulb here, even when you close the switch, the voltage here stays the same. After all, the voltage here has to be equal to the voltage across the battery. So the argument goes like this. Closing the switch here doesn't change the voltage here. Therefore, the voltage stays the same. Therefore, the brightness of this light bulb does not change when we close the switch. So we have two conclusions that are different. They cannot both be right. So there's a flaw in the logic here. It's quite subtle what the flaw is, and I will ask you to pause the presentation now and try to figure out what the solution is. But it's quite tricky. Okay, so let me explain what happens. It turns out that argument 2, well, they're both correct up to a point, but argument 2 is the most solid one. So it is true that delta V remains the same across light bulb A, so the brightness of light bulb A does not change. This light bulb here, the brightness doesn't change when you close the switch. That's the correct answer. So what's the problem with this statement here? The current splits at this junction here. That's true. For sure the current will split. But then the problem is to say that because the current split here, there will be less current in that resistor than before. This is the flaw in the argument. Why is it wrong? That's a bit subtle. So let's look at that. When we connect we close the switch here, what happens to the overall circuit? Where, well, you've changed R equivalent, right? You've connected two resistors together in parallel, so you've changed the value of R equivalent. So what's the new R equivalent after the switch is closed? Well, it's before the switch was closed, R equivalent was just R because it was only light bulb A, right? So before the switch was closed, we have only this part of the circuit here. So the only resistance was R, and therefore the current was just E over R. Okay, that's before we close the switch. Okay, after we close the switch, the switch R equivalent now is given by R1 over R plus 1 over R to the minus 1, right? Because they're in parallel. So you calculate that, you get that R equivalent is R over 2. So notice we close the switch, we include the new resistance, which is the new light bulb, but this has the effect of reducing the R equivalent. Okay, this is subtle. We added a resistor, we added a light bulb, and the net effect is to reduce R equivalent. Now, because we've reduced R equivalent, the current now flowing out of the battery when the switch is closed is now the EMF divided by R equivalent, which is R over 2, so we get 2E over R. Notice this result here. The current flowing out of the battery now that the switch is closed is twice the current that we had before we close the switch. So here's what's happening. When we close the switch, the current that flows here, before we close the switch, the current here was E over R. When you close the switch here, the current that flows out of the battery here is now given by this value, 2E over R. So the current here flowing out of the battery when we close the switch it doubled. Okay, so before we had E over R, now we have 2E over R. So the current here doubled when you close the switch, and now the current goes here. Because the two resistors are equal, the current here splits in two exactly. E over R goes down, and E over R keeps going and goes in the other light bulb here. So look at this. The current that goes to this light bulb here is exactly the same current that it had before we closed the switch. So the current flowing through light bulb A has not changed. Even though the current here does split, is split in two here, the current in the light bulb does not change because the current coming out of the battery has increased. Okay, so that's the solution. Delta V doesn't change, so the brightness stays the same, and actually I does not change through light bulb A. The I stays the same as before, so the brightness doesn't change. So closing the circuit, closing the switch here has actually increased the current coming out of the battery. So that's important to remember. Current coming out of a battery is not always the same value. It depends on what the battery is connected to. So this is an example where connected this way here, adding a resistor here has the net effect of increasing the current coming out of the battery. Okay, so that's the solution. Now, just a little comment. Notice that what happened here, we added an extra resistor in parallel, and what it did is that it decreased the equivalent resistance of the circuit. This is a general rule. You might not have realized that, but when we combine resistors in parallel, the equivalent resistance is always smaller than the smallest resistance that we combined, that was combined. So just to make that clear, let's say you combine three resistors in parallel: R1 10 ohms, R2 5 ohms, R3 2 ohms. Calculate R equivalent when they're in parallel. Okay, I'm doing parallel combination here. When they're in parallel, you do 1 over R1 plus 1 over R2 plus 1 over R3, all that to minus 1. You get this, 1.25. Notice that R equivalent is smaller than the smallest of the three resistors, which was 2 ohms. And this is always true. When you add resistors in parallel, you always decrease the total resistance. Okay. Now, another example here. Let's say we have a light bulb here, and I move another light bulb, and I'm going to, let's say we insert this light bulb here in the circuit, so we add it in series with light bulb A. If we do that, what happens to the brightness of light bulb A? Well, this example is very simple. When you add this light bulb here, now because they're in series, the R equivalent will increase this time, okay, because they're in series. R equivalent increases, therefore the current coming out of the battery will go down because you have more resistance. R equivalent has gone up. So the current flowing here has gone down. Therefore, the brightness of light bulb A has decreased. Okay. So adding a light bulb in series will have for effect of decreasing the brightness of light bulb A. Another example. We're connected this way. You have light bulb A here, light bulb B. And we close the switch. Sorry for this. Okay, we have a switch here. And then we close it like this. So initially when it's open, there's no current here, so this is off. And then we just have current flowing here in those two light bulbs. Now we close the switch. What will happen to the brightness of light bulb A, and what will happen to the brightness of B? That's a bit more tricky. Focus on A first, okay? That's easier. So try to make your prediction before I tell you the answer, okay? So what's the answer? You close the switch here. Again, the key point is what happens to the current flowing here? Well, notice because we added this R here in parallel with this, when I close the switch, so now we're doing when the switch is closed, okay? So light bulb, this one is emitting light, okay? When the switch is closed, notice the resistance of this part here has changed, right? Because you have two resistors in parallel. So before you only add this B with resistance R, but now you have R equivalent for those two here is R over 2, right? Now look at the total resistance of the circuit. Now you have R plus those two in parallel. Because they're in parallel here, like we just learned, putting two resistors in parallel will decrease the resistance. Therefore, this battery here sees a total resistance which is smaller than before. So closing the switch has decreased R equivalent of the circuit. If R equivalent decrease, the current flowing out of the battery has increased, right, when we close the switch. Closing the switch will make this current go up because R equivalent decreased. So if the current flowing here has gone up, that means that the brightness of light bulb A increased. Now, what about light bulb B? When I close the switch here, we just said that the current flowing here has increased. In this branch here, it went up. But now you have a larger current, but when it reaches this point, the current will split here and here. It splits in two. So it's not clear what happens to light bulb B. On one hand, there's more current here, but now then you split it in two here. So will the brightness of B increase or decrease? I'll let you try that, and you should find, you can do the calculation, calculate the current flowing into B, and compared to the current before when the switch was open. And you will find that actually the brightness of light bulb B actually goes down when we close the switch. So the brightness of A went up, the brightness of B went down. I'll let you try that. Thank you.